Almari-Bynum-Goans-Thomas, and I'm wearing the required PPE, hard hat, and safety glasses.
I'm David Bynum, and I'm wearing my safety glasses and a hard hat.
I'm Brooks Jones, and I'm wearing my safety glasses and hard hat as well.
Hi, I'm Mushal. I'm wearing my hard hat and my safety glasses.
Okay, this is the main valve that we use for our 2-tank water system. We turned it all the way down to get it going. And these are the 2 valves that led to the tanks themselves. Black one turned all the way to the left for it on, and the butterfly valve in red turned vertically to have it on. This picture is the top of the tank, and what I have highlighted in yellow is the valve that we use to control the flow into the top of the tank and ultimately to achieve steady state. This is the valve at the bottom of tank 1. We just pulled it all the way down to drain into tank 2, and then this is the bottom of tank 2. The valve that's highlighted in yellow just led to a drain. Okay, for this part we just recorded about 10-second intervals of both tanks, the top and the bottom, and we recorded them at a certain point in time, and then 10 minutes later recorded them again, and as you can see, the change in the water level doesn't move over those 10 minutes. So that's how we knew that our system was at steady state. Okay, for this part we just showed mathematically how our system was at steady state. We started off with the mass continuity equation. dm dt equals d dt times the integral of density. dv equals negative the integral density of the dot product of the velocity vector times the normal vector times dA. Then taking the integral of the left side and the right side, you're left with dv dt equals qin minus q out. What we did at the top was the 2 densities canceled, and then when you take the integral of dv, you're just left with v, so v times d dt, you're left with dv dt. Then from our homework, we've seen in chapter 3 that the volume is equal to the cross-sectional area times the height. So we use this as a resource, and taking the derivative of that, you're left with dv equals the cross-sectional area times dh. Now plugging in that for dv on the left side of our equation, you have the cross-sectional area times dh is equal to the flow in minus flow out dt. Just multiplied dt on both sides from the left hand side and the right hand side, and it canceled on the left hand side. Then we took the integral of both sides. For the left, we had the interval for our time. So we started for the lower limit, we did t final, or t initial, sorry, and then t final for our upper limit times dh equals our flow in minus flow out divided by the cross-sectional area times dt. looking for a change in height. So we went ahead and wrote that as delta T is equal to flow in minus flow out. And for our dt, or change in time, we just wrote that as our T initial minus T final, or I wrote in here as T1. And then showing that we saw in the video, the change in heights didn't change over time, so it was 0. And then solving for the right hand side, we got 0 equals flow in minus flow out. And then just bringing just solving for that, you get that Q in equals Q out.